All right, good morning. Okay, we'll start. Okay, so today we have quite a big lecture. So there will be no exercise session, just one long lecture. So we'll try to cover everything. It's quite an important lecture for the course. We'll be talking about how can we reason over time. And so the goal will be to see if we can not only deal with environments that are only partially observable, okay, that we have seen, we can cast that as an inference problem about all the variables that we assume but we can't observe, and we can do inference to try to estimate them from observed variables. What will be different today is that now we'll also assume that the environment is evolving with time. Okay, so we'll have to account also how the environment evolves to update our beliefs about all the variables in the environment that we can't see. Okay, so in summary, the goal will be to try to maintain a belief state about the world or the environment, and then also to be able to update this belief state as time passes, and also, of course, as we collect more and more observations. Okay? So we'll be building upon what we have seen in the previous 2 weeks. We'll use Bayesian networks to represent this kind of systems. And we also solve this problem by just framing it as an inference problem. Okay? So the class of probabilistic models that we'll consider today are called Markov models. So I will introduce what they are. We'll go over Markov chains, hidden Markov models. We'll also define the various inference tasks that we can define on top of that. And basically, the main family of inference problems we'll see today are the so-called filtering problems, in which we just want to estimate the current state of the system as we collect evidence. Okay? This lecture is quite important, as I said. In the second project, this is exactly what you will have to implement. You will have to implement a Pac-Man agent that will have to chase the ghosts, but it will not be able to see them directly. Okay? And so the scenario will be something similar to this. So let's assume that we have a regular grid world in which we have Pac-Man. And this time, the goal of Pac-Man is not to eat all the food. There is no food in this maze, but there are 4 ghosts somewhere in the maze. These 4 ghosts, you can't see them because they are ghosts, they're invisible. But what you do have access to is some kind of radar, some kind of sensor that you can use to probe how far is the ghost from Pac-Man. Okay? So you will have access to noisy measures of distances from Pac-Man to the ghost. And from these distances that you see there at the bottom, your goal is to try to find them. Okay? So you get these 4 numbers. The ghosts, of course, are moving. And the goal for today will be to try to see if we can make sense of these observations as we collect them through time to actually locate the ghost. So by chance, here we just got one of them. Okay? But from these numbers, we'll see that we can actually locate them, and when we'll see how to do that, you will see that then the game is quite easy to solve. If you just have access to this maze with the 4 distances, as humans, it seems quite difficult to locate the ghosts. At least I can't see them. Can you see them? So we'll see that actually when we model that as an inference problem and we keep updating the plausible positions of the ghosts given the distances that we have observed, then it will become super easy to solve. Okay? So that's the goal for today, to try to solve this kind of problems. All right, so before we do that, I have to introduce a few theoretical concepts. The first one will be the class of Markov models. Okay? So in a Markov model, we'll first make a very big but simplifying assumption, which is, okay, we have this environment which evolves through time, instead of assuming that the environment evolves continuously with time, we just assume that the time is simply a series of discrete time steps. Okay, so we discretize the time dimension. So we'll consider that the world evolves as discrete time slices, and each of these time slices will contain a set of random variables. Okay, so today we'll be dealing with two sets of random variables. We'll have one or several variables that correspond to everything about the system that we can't see. So that will be the state of the system. Okay, and I will index these variables with the letter T. Okay, because I will have one variable for each time slice of the environment. Okay, for each time step, I will have one of these variables. Okay, so these correspond to the state variables. They are not observed. However, we do have access to observations, evidence, which I will denote similarly, but with another variable, E, for the evidence, and I will have one evidence for each time step. Okay, so we have these two sets of variables, and what I'm just saying is that this, if the world evolves, it means that at the next time step, I will have xt plus 1, I will have et plus 1, and so on and so forth. Okay? And each segment will correspond to a time step. Okay? We'll assume that we have a prior over the initial state of the system. Okay? So we'll assume that we have defined a priori the plausible values for the state of the system at the very first time step. So x0, we have a probability distribution that defines our initial beliefs about these initial values. Then we'll assume also that we have a transition model. So transition model will define a probability distribution of one variable, one state variable, given the previous ones, xt, xt minus 1, xt minus 2, and so forth. Okay? So, for example, so let me just rename this. Sorry. T plus 1. Okay, so we'll define the conditional probability distribution of xt given the previous variables. So we may have also xt minus 2 here. Okay, and all the others that happened before from x0 to xt minus 1. Okay? And similarly, we'll also assume that we have a sensor model that defines the conditional probability distribution of the observation variable at time step t, and this conditional distribution will be conditioned on everything that happened before. So meaning the current state variable and all the previous state variables. And similarly for the observations, et minus 1, et minus 2, and so on and so forth. Okay? So this will define P of xt given x0 t minus 1. And here we'll have P of et given the previous state variables up to t, so from 0 to t, and the previous realizations of the observations from 0 to t minus 1. Okay? So this conditional probability distribution is what I call a transition model, and this is what I call the sensor model. Okay? The transition model will basically define in a sense, the physics of the environment, how the environment evolves. And the observational model or the sensor model will describe how the observations are being generated or emitted from the state variables. Okay? Okay. So this is very generic, but today we'll make simplifying assumptions. And the assumptions that we'll make are the Markov assumptions. So we'll assume that the current state of the world depends only on its immediate previous states, one or several previous states, but not, it will not depend on all previous states. Okay? And typically, the assumption that we'll make is that the current state xt depends only on its immediate previous state xt minus 1. Okay? So in that case, the model simplifies. I can remove all these arrows there. I just have a conditional distribution for xt defined with respect to xt minus 1. Okay. So if you make this assumption, what happens is that these state variables, they are connected like this, and they form a chain, okay, which we call a Markov chain, okay, or a Markov process, which is basically simply a series of variables describing, for example, the state of the system, and we are assuming that the current state of the system depends only on the previous state and only the previous state, not everything that happened before that previous state. Okay? So if you do that, what you get is what you call a first-order Markov process. But you could generalize that and say, for example, that xt depends not only on the immediately previous one, but also on the previous. In this case, you would have a second-order Markov process. You can always make that. But to be honest, you can almost always reduce your probabilistic model in terms of Markov processes by just combining variables. Okay? So we have this. We have a Markov chain describing the evolution of the state of the system. We also make a similar assumption regarding the sensor model, and we'll assume that the observation at time step t only depends on the current state xt. In which case, that means I can just remove also all these arrows. And remember what I said last time, when I'm removing arrows, it's also equivalent to just making conditional independence assumptions. Okay? And in this case, we would have the sensor model, which simplifies to P of et given x. Okay, so we make two Markov assumptions. One for the evolution of the state of the system, and another assumption for the relationship between the observations and the states. Okay? And we are just saying that ET is conditionally independent on all the other variables given x. Okay? And finally, we'll make a third assumption, which is a stationarity assumption, which is to say that these conditional probability distributions that I use to either describe the evolution of the system or the sensor model, they do not depend on t. Okay? So the dynamic, the physics in a sense of the environment is fixed, and the same for the observation model. In the sense the instrument, for example, does not degrade with time. Okay, it's not a function of time. Questions on this? Okay. Okay, so in this form, what you should see is that we are just dealing with some kind of Bayesian networks, which is a bit peculiar because now the structure of this Bayesian network is potentially infinite. It's like a growable Bayesian network which grows with time. As you add more and more time steps, you add more and more variables to the Bayesian network. Okay? But if you just see that as a Bayesian network, then it becomes obvious to define it also its joint probability distribution. So the probability distribution over all the variables that you see there in the diagram. And we'll have that the joint probability distribution, so we have the state variables, x, from 0, the initial state, up to the current time step, t, together with the evidence, the observations, going from 1 to t. Yeah, usually in these slides I will assume that I do not have evidence for x0. I start collecting evidence for xy. Okay, so this is the joint distribution over two t plus 1 variables, and this can be written using the diagram. So you can refactor this joint as first the prior beliefs that you have on x, px0, and then you have p of x1 to t, which we can factorize using the transition model. Okay, so to go from x0 to x1, we have to make one stochastic transition. Okay, through this model, and so we can define the conditional probability distribution of x1 given x0 by just using our transition model. And we can do that for all the time steps. So here we'll have a product from I equal 1 up to t of the conditional distribution of xi given xi minus 1. So we just make t transitions. And then for each, we also observe some evidence. So for each xi, we get to observe ei, which happens with the probability given by the sensor model, P of ei given xi. Okay, for everyone so far? Okay. An example which is used in the textbook and which I will use today is this very simplified weather model in which, let's say, we want to reason about the weather. And so the weather would correspond to the state xt. Okay. It could take, for example, two values to simplify even further. Either we have sun or it's sunny or rainy. We can define some prior probability distribution for this state. We can also define maybe a transition model for that, which would be given here. So the probability of, so if the state is given by some rain variable, binary, we would say that if it was raining before, the day before, at the time step before, at t minus 1, the probability of rain at time t is 70%. And of course, the probability of no rain given that it was raining at the previous time step is the complement, so 30%. And on the other hand, if it was not raining at time step t minus 1, then the probability of rain at time step t would be 30%. Okay, and vice versa also. Okay? Then we can make or consider some artificial sensor model, in which case the example that they take is whether or not you take some umbrella at the corresponding time step. Okay, so if it's raining, then the probability of you taking your umbrella is 90%, but you may forget it with 10% probability. And if it's not raining at time step t, the probability of you taking the umbrella is only 20%. Okay? And so with these three components, a prior, a transition model, a sensor model, we have this, okay? And then once we have this as a Bayesian network, we can start asking questions or queries, or we can do inference on this network. And so, for example, you can ask this query: what is the probability of the umbrella at time step t if it's running at time step t? Well, in this case, it's immediate because you can just read that from the sensor model. What is maybe more interesting is that let's assume that you only observe the umbrella variable. Okay, you cannot go out and see the weather. You just see whether or not, I don't know, someone took this umbrella or not. And then you ask, okay, given that I've observed a sequence of realizations for the umbrella variable from 0 to t minus 1, what is the probability of rain for the next day? Okay? Or another interesting question you may ask yourself is, okay, if I see that it's raining today, okay, that rain at time step t is positive, what is the probability of rain tomorrow or the day after? So how would you answer these kind of questions? Okay, so that's what we'll try to see today. Okay, the transition model can also be represented also in this way as a diagram where the nodes do not correspond to variables but correspond to values that the variable can take. So for example, here for the weather problem, we would have one variable rain which can take two values with two nodes, rain and not rain, or rain and sun. And then the arrows represent the probability of transitioning from one value to the other. Okay? So this table that you see there can be equivalently represented in this way. Okay, so now that we have defined this, what are the inference tasks that we'll try to solve today? The first one is what we call a prediction task, which is basically forecasting. So if you make a sequence of observations up to time step t, so if you observed E from 1 to t, then the goal of prediction will be to try to estimate. So let's say you observe this and all the ones before. Then in a prediction problem, the task is to try to, given these observations, and only this observation, you don't observe the xt variables. Then what you want to do is to try to estimate the conditional probability of future states. Okay, so for example, of xt plus 1, xt plus 2, or xt plus k in general for k larger than 0. So that's what we call prediction or forecast. Then we have the filtering task, which is not about trying to estimate future state, it's just about trying to estimate the present state. Okay? So here, the goal will be to try to estimate the conditional probability distribution of the current state xt if we do observe a series of observations from 1 to t. Okay? And so this is exactly, by the way, what you will have to implement. You will have to solve a filtering problem when you will have to implement Pacman, because what you will have to do then is, given a sequence of observations in the form of these tuples of distances from Pacman to the ghost, you want to estimate the state of the system. In this case, you want to keep an estimate of the actual positions of the ghost somewhere on the grid. Okay? Accounting for the fact that these ghosts will be moving, they can be moving at random, or they may follow some policy, but you will be able to implement that in the transition model that you have. Okay, so that's filtering. Then we have smoothing. Smoothing is it's similar to prediction, but in the past, it's trying to estimate or to recover the state of the system for some time step t minus k if you observe a series of evidence from 1 to t, okay, and t minus k is some value of the time step before t. Okay, or xk here. And finally, the last problem we'll try to solve today is to try to retrieve the most likely explanation. So if we do observe a series of observations, one thing we may be interested in, of course, is to try to recover the posterior probability distribution over the trajectories of the system, so the joint values of the state of the system. But that's actually quite difficult. A simpler problem is to try only to extract the most likely explanation, the most likely sequence of states from 1 to t that are compatible with the observations. Okay? Questions on this? Do you all understand what we want to solve today? Okay. All right. So there are two things that we'll use over and over today, which are summarized in this slide. The first thing is what we call a push forward or predict operation, which is to say, given that you may have some initial knowledge about the state of the system, P of x1, what will be the marginal distribution of x2? So if you assume that you know, or that you have a marginal distribution describing the probability of the state at xt minus 1, so you have this. Okay. Can you use this together with that, then to obtain the marginal distribution of xt? Okay. And what I will say often today is that, okay, given some initial beliefs, what would happen if you push forward these beliefs one step through time, through your transition model? How will this probability distribution evolve at the next time step? Or to obtain the next time step. Okay? So this will be a predict step. And what we'll have is that if we start, so the predict is to start at x1 and to obtain p at the next time step, p of x2. How do we do that? What we'll have is that p of x2 is equal to the joint distribution over the two variables, x1 and x2, but for which we have marginalized out x1. Okay? So we just have to iterate over all possible values of x1. Okay? And we'll obtain the marginal distribution for x2. Okay? So this can be written using the structure that we've assumed as a sum over all possible values in the previous state, x1. For each of them, we associate a prior probability. That's exactly p of x1. And then we just push forward this possible state value through the transition model to obtain a conditional distribution of x2 given this particular value of the state x1. So. Okay, is it clear for everyone? So for example, in the case of Pacman, you may have a ghost, or you think there is a ghost somewhere at this position. Then if you think with 100% certainty that it's there at this position, but then if you say that, okay, but at the next time step, the ghost can move randomly, then it could be in this cell, or in this cell, or maybe also in this cell. Okay? And so in this case, you will predict, and what you will obtain is the marginal probability distribution of the ghost position at the next time step. Okay, and you just enumerate, in this case, all possible next time steps. Okay? Clear for everyone? Okay, so that's the first operation we'll use. And the first one, so this is something, by the way, for which we only require the Markov chain. Okay? So given some belief, initial belief in the form of P of x1 and the transition model, we can make this prediction. The next second operation we need is the update. So if we have P of x1, we have some prior beliefs about x1, and then we receive some observation E1. Then what we want to do is to use this observation to update these beliefs. Okay, so in an update, what you want to obtain then is P of x1 given the observation. How do we do that? How do we go from some initial prior belief to a posterior belief about the same variable after having observed E1? Yes?
Bias rule?
Yeah, okay, I'm listening.
P of x1. Px1 E1 when switched. And then over P of E1.
Yes. Okay, so we can make this update using the base rule, in which we start from the prior, which we had. Then we reweight this prior by the likelihood of the observation, P of E1 given x1, and then we normalize by the evidence P of E1. Okay? And after that, we have the posterior about the state variable x1 given that observation. Okay, so everything we'll do today is just always a composition of these two mechanisms. So if you understand that, you should be able to rederive by yourself everything we'll see. Okay, so now that we have this, we can start trying to solve these four inference problems. So we'll start with the prediction problem. We want to estimate or to forecast or to predict the state of the system into the future. Okay, so we want to obtain the conditional distribution of xt plus k given some observations up to t. How would you do that? Well, one thing which we can do, very simple, we can assume that we have some prior beliefs about the current state of the system, p of xt given a sequence of evidence from 1 to t. Okay, and we'll see how to obtain this thing in the next inference problem, because this is itself a filtering problem. But assuming we know how to solve this, assuming we know how to filter, then if we want to obtain the conditional probability distribution of the states into the future, then we can start from these prior beliefs that we have about the current state, and then we just have to predict or to push forward these prior beliefs k times through the transition model. Okay, so you take this conditional distribution or this distribution, and then you apply this prediction step k times, and you will obtain the prediction probability distribution p of xt plus k given the evidence values. Okay. So mathematically, we can define p of xt plus 1 given a sequence of observations up to time t. How? We start from our prior beliefs, p of xt given the evidence variables, and then we push it forward once through the transition model. Okay, so through p of xt plus 1 given xt, and then we just have to integrate over all possible values of the state at time step t. Okay, and that will provide us with the conditional probability distribution of the state of the system at the next time step, given a sequence of evidence up to time t. And if we can do that once, then we can just repeat this process a second time. We would then obtain, starting from this prior belief now, we just push it forward again, and we would obtain p of xt plus 2 given a sequence of evidence up to time t, and we can repeat that over and over until we reach p of xt plus k given the evidence. Okay, so this is an example of that. If you remember, this is the example we use to try to locate the position of the ghost on a grid, starting from a uniform belief about its position. Then we can collect some evidence. Okay. Let's say this is your current belief. And then you can try to reason what would happen now if you let the system evolve through time. If you don't observe anything yet, if you don't observe anything anymore, but just let the system evolve, so the ghost will move somewhere on the grid. Okay? And if you make assumptions about how the ghost could move through your transition model, then you can update this belief into the future. Okay, so let's see. So here, this is what would happen if you assume random moves. So, okay, 1, 2, 3. Okay, so how do you explain this? Yes?
At the beginning, you choose the real position of the ghost? Or
We don't know the real positions. We are just talking about our beliefs.
okay, so it was the belief of position.
Yes, so around here. This is your current belief. And then eventually we simulate time steps. And when we simulate, we update, we make prediction steps for each time step into the future. Okay, so we start with this prior belief in which it seems that we are quite confident about the position of the ghost, but as we look further and further into the future, we observe this. Okay, so what's going on? Yes?
So each time the ghost or whatever moves, well, he has new choices. So each time it moves, we are less and less. Well, we know less and less because each time he moves, he could be in many more places than before.
Yeah. So if we assume that the ghost can make random moves and we stop collecting new evidence, then we are basically losing track of where it could be. So we are more uncertain about its actual position, and that translates with lower probability values for each of the possible positions. And eventually, in this case, if we were to simulate for very, very long horizon, we would go back to uniform probability values. Okay? However, what I want also to stress is that it's not always like this. You will not always necessarily be more uncertain. The evolution of your uncertainty will depend on the transition model that you assume. So for example, if you assume that the ghost is still somewhere on the grid, but now instead of making random move, it's going in circle inside the grid, then as we simulate forward using the prediction equation, the evolution of our belief state, if we assume, for example, that the ghost is going clockwise, then this is what we would observe. So what you see there is that if you make stronger assumptions about the transition, then your uncertainty will decrease still, but more slowly than before, and it will have some interesting dynamics, as the one that you see there. If you assume that the ghost is going in circle, then of course your beliefs will also go in circle. Okay, but eventually you also see that it's disappearing in this case. It's not always disappearing. That depends again on the transition model. If you assume that the ghost is going in spiral and eventually reach the center, then what do you think would happen to the prediction probability distribution? Yeah.
Eventually, you have a 1 probability.
Yeah. So if you assume that the ghost is going in spiral and eventually centers around this location, then whatever your initial beliefs, if you just let the system evolve sufficiently many steps, you will then be quite confident that it's somewhere there at the center. But we can just check that. Okay, and you see there that whatever the initial values, eventually we believe that it's somewhere there in one of these two cells. Okay, so what we've observed from these three examples is that as time passes, usually uncertainty will increase or certainty will decrease, so the probability values will decrease if you don't observe any new evidence. Okay, so of course that's, as I said, that depends on the actual transition model that you assume, but for most transition models in realistic scenarios, usually you will have that the uncertainty will increase as you stop collecting new evidence. Okay, so now that we have this, there is an interesting question that we may ask ourselves is, what would happen at infinity? If we were to apply this prediction step infinitely many times, what is the probability distribution that we would reach? Is this something special or not? So what would happen as t grows to infinity is that for most chains, the influence of the initial distribution, so of the prior p of x0, will get lesser and lesser, okay, over time. And more interestingly, eventually the distribution may converge to a fixed point. Okay, it will converge to a fixed distribution, which we call the stationary distribution of the Markov chain. Okay, and how do we define this distribution, or what is the property of this distribution? It's a distribution such that when you push it forward through your transition model, you obtain the same distribution as initially. So mathematically, it's a distribution that we will denote as p of x infinity, such that the distribution of p of x infinity is the same as the marginal distribution at the next time step, p of x at infinity plus 1. Okay, and that would happen if these two equations are true. Okay, so if you start at p of x infinity, you push it forward once through your transition model, then you marginalize out the x infinity variable, you obtain p of x infinity plus 1, and if this distribution is the same as the initial distribution, then what you have is a stationary distribution. Okay? It's stationary because when you push it forward through the transition model, it does not change. Okay? It's still the same. So for example, for the weather problem, if we assume this transition model, if the probability of rain, the probability of rain today, given that it was raining yesterday, is 70%. The probability of sun, given that it was raining yesterday, is 30%, and so on and so forth. Then you can quite easily obtain the stationary distribution of that chain, not by simulating infinitely many times this prediction step. You could, okay, and eventually you would see it converge. But you can analytically obtain, in this case, the stationary distribution. So what we need is simply to solve this equation. So we just impose that P of x infinity given sun should be the same. So the probability of sun at some time step should be the same at the next time step. Okay. Then we use the structure of the Bayesian net of the chain that we assume. The next time step is the previous time step going through the transition model. Okay. And so at the previous time step, it could be either we could start from sun and then arrive also to sun. Okay, so that could correspond to this first term. Or we could start from rain and arrive to sun. Okay, and that would correspond to this. Okay. Then we replace the conditional probability term by their actual numerical values. So 0.9 here for this one and 0.3. Then we have this equation, which we solve. Okay, and we arrive to this constraint that the probability of sun should be equal to 3 times the probability of rain. Okay, then since we know that probability value should sum to 1, we are good to go and we can solve this. And the solution will be such that the probability of sun should be 3/4 and the probability of rain should be 1/4. Okay, and now these two probability together define the marginal probability of x infinity, and that's the stationary distribution. Okay, you can check by yourself. If you start from this probability distribution, you push it forward once through the transition model, then you obtain the marginal probability at the next time step. You should get back the same initial values. Okay. Questions? Okay, so I think so I will do a break now for 10 minutes because then we'll move on to a bigger piece, which is the filtering problem. Okay, so let's go back here in 10 minutes. All right, we'll continue. Okay, so as a very quick recap, we are assuming that we are dealing with this kind of probabilistic model in which we have a system defined or described by some state variables x, which we can't observe directly, but which we assume to evolve through time according to some transition model, okay, which we also assume to be Markovian. Okay, and so these variables x, they form together a Markov chain, and we make a second assumption is that we also observe other variables, evidence variables, and we observe we have access to one evidence variable per time step, okay, and we assume also a Markovian sensor model, okay, so we get that E1, for example, is conditionally independent on everything else given x1, okay? Then we started thinking about inference tasks that we want to solve. The first one is the prediction task. If you start with some belief about the state of the environment, can you predict its evolution, k step into the future? Okay? And to solve this problem, I've been telling you that we'll be only using these two operations today. The first one is the prediction, which you can use to push forward a distribution on the state variables one step into the future. And the second one is the update, which you can use to update some belief distribution that you may have about the state variable, given now an observation that you collect at that time step. Now, how can we solve the first problem, the prediction problem? So if we want to estimate p of xt plus k given a sequence of evidence up to time t, we'll make an assumption that we can compute or estimate the current state of the system, p of xt, given everything that we've observed so far. And then, to make projections k step into the future, we just have to apply the predict operation k times. Okay? And we will obtain this conditional distribution of the future state given evidence up to now. Okay. The next inference task is the filtering task, which is basically trying to deal with observations we'll have not continuously, but which we'll collect at each time step, and which we'll have to use to update our current beliefs. So the question is, if this is your current belief, and then there is one step which happens, in which the system has evolved, and at which also you have made an observation, how do you go from your initial beliefs to the updated belief for the next time step, and given also the new observations that you have collected at that time step? So what we'll do is to implement a function, f, that starts with some beliefs that you may have about the current state t, and given everything that you observed up to t. Okay, and what we want to compute, or what we want to do, is to update this belief given the new evidence that we observe at the next time step. Okay? So basically what we want to obtain now is the conditional of xt plus 1 given everything that we've observed up to t, and also including that new observation, et plus 1. Okay? Well, actually, when we decompose the problem in terms of these two operations, it should be quite straightforward. In order to obtain this conditional distribution over the next over the state at the next time step given et plus 1, what you have to do is to take our initial beliefs, which we assume we have for the current time step up to t. We push it forward once through the transition model using a prediction operation. And then we make an update through this projected belief using this update operation. Okay? So you can make a prediction for the next time step that would give you p of xt plus 1 given. So we start from this. That's our current belief. We do a projection. We do a push forward through the transition using a predict step. That would give us now p of xt plus 1 given et. Okay. And then we do an update like this using et plus 1 to obtain this conditional distribution. Okay? So a filter, or more specifically a Bayes filter, is simply the combination of these two operations. So you push forward once your current beliefs, and then you update these projected beliefs using the observation. That's it. Okay, so how do we have to implement f now? Okay, the first thing is that I will just divide these observations into two sets. The evidence that I've already considered up to t, and that new evidence that I have to integrate, at t plus 1. Okay? Now, this so how can I go further now? So I can swap these two terms like this using the Bayes rule, or the conditional Bayes rule in this case. So I would have P of dt plus 1 given xt plus 1 and given that condition, which remains there, times the prior P of xt plus 1 given E1. Okay, and I need to normalize that by some constant. Okay, now this, because of the Markovian sensor model, Et plus 1 is conditionally independent on all these variables, given its parent, given its state variable. So this can be simplified to Et plus 1 given Xt plus 1. Okay? And now this, what is this? This is the same as P of xt given this projected once through the transition model. Okay, so we start from some unknown xt, and that happens with the probability of P of xt given the evidence up to time t, and then we make a transition to reach xt plus 1. Okay, and here you should see that we have a recursive relationship because P of x, so what you should realize that P of xt plus 1 given observations up to t plus 1 is something that I've re-expressed as a function, this function, which depends on my beliefs about xt up to t, okay, which is the same as this, but just with one time step before. And then this is given, this is my transition model, and this is given, this is my sensor model. Okay, to be complete, I need to define z. So in this case, it's P of E t plus 1 given E from 1 to t. Okay. Questions? So this is the Bayes filter. This is the equation you should remember today. I'll just do it here. Okay. Is it clear for everyone? Just one thing you should pay also attention to. So you should notice that for some of the variables I'm using a capital letter, and for others the lowercase. Okay, this is not a typo, okay? Because here I'm really conditioning on some particular value, lowercase, but here I'm interested in the conditional probability distribution of the variable for all its possible values. Okay? So this is a distribution, this is a scalar, and this is a distribution, so, or conditional distribution in this case. And the whole thing is a distribution. So in the discrete case, this is a table. Okay, so you have the development of the slides, the same as the one on the blackboard. Another way to think about this problem, and that's an analogy they make in the textbook, is that you can also think of the estimated state up to t as some kind of message, f, which they call f from 1 to t, which you propagate forward through the sequence. Okay, so these messages are being changed, modified by each random transition through the transition model, and then updated after each observation. Okay, and so that means if you, for example, want to actually implement that on a computer, you can just reason in terms of these messages, which are just a representation of these probability distributions as a table. And what you have to do is to implement this f or forward function, taking as input the current estimate up to now, up to t, and then integrating this new evidence. Okay? All right, so let's do an example on this problem, the weather problem. Okay, so I will just reproduce these two tables there so that I can see them. We have and false. Okay, and the other one, conditional. Parti. And false. Okay, so we'll do a yes.
0, 1. It's not 0, 1.
No, it's not. Okay, can anyone explain why this is not a mistake? It's a good question. Yeah.
Usually it's before the first is the case, we have an umbrella against the rain, and in the other case, it's not the contrary as
here. So basically here it's a condition, what changes here RT is the value of the conditioning variable. Okay, and so I'm just writing down the conditional probability of the positive value for UT given this value for RT. Okay, so this, when you condition to true, you get some conditional distribution for UT, and when you condition on false, you get some other distribution. Okay, but they don't have to match. They are two distinct distributions. Okay.
So on your slide is RT, PUT, yes?
Yeah, in this case they do happen to match, but I could have picked another transition model in which these two values do not sum to 1. Because again, this is a conditional distribution.
And the next, next table is RT, PUT, and RT is the same as UT?
Yeah, it's this. Yeah, I should fix the slide. It's conditionally on RT minus 1. Okay, so the goal will be to try to compute P of R2 given two positive observations of the umbrella variable. Okay? You observe the umbrella twice, and then you want to reason about whether or not it's raining at the second time step. Okay? So that's a filtering problem. So it seems we can use what we've seen. So we'll start with the prior, P of R0, and I will assume initially that I have a uniform prior, which I will denote as 0, 5, 0, 5. Okay, I'm just using this notation to denote the whole tables. Okay, and the first will be the positive the probability associated to the positive value, and the second to the negative value. Okay, what do we have to do then? We transition to time step 1, for which we observe U1. So the first thing would be to push forward our prior beliefs one step into the future using a predict operation. Okay, and we have that we start from some value R0, we don't know which, with some prior probability PR0, and then we make one step transition to arrive to, R1 given R0. Okay. And then this sum, P of, so we have two values, positive, negative, each with a prior probability of 0.5. So we have 0.5 times the conditional probability of R1 given positive rain. So this is what is given. We are there in this row, so it's 70% probability, and then the complement. And then we have the negative value with the same prior probability. Then we read this row now. The positive value for the rain would have a 30% probability and 70% for the other. Okay, so we have 0.35.15 plus okay. Next, we observe U1. Okay, so we have some prior beliefs about R1. We make an observation. We can use Bayes' rule or this update operation to integrate this observation. So we know that this is proportional to P of U1 given R1 times our prior beliefs about R1. Okay? So this is equal to P U1. So this is given by this. Plus times, sorry. Okay, and now if we normalize, we get okay, and in terms of these messages I was talking about, this is F11. Okay, but we want to reason about the range variable at the second time step, not the first. So what do I have to do next? So I have some belief about the range variable at time step 1, but I want to go there to determine the conditional probability distribution at the second time step, given two evidences. Okay, so we can take these beliefs and then project it once again through the transition model, and what we would have then is P of R2 given U1, which then we would have to update given the second piece of evidence, and we would be done. Given U1. So we have to start from some position R1, okay, which we believe to have a probability of PR1 given U1, okay, and then we push it forward once through the transition model, which gives us the condition of R2 given R1, okay, and we have to integrate over all possible initial values of the states. Okay, what is PR? So for positive range, positive umbrella, what's the numerical value? Is this one, which we have just computed there. Times this, P of R2 given R1. This is given by the transition model. So this is assuming positive R1 plus we have to consider the other case where R1 is negative. We think that happens with a probability of 80%. And then when it's negative, we do a one-step transition to reach the next time step, 0.3, 0.7. And when you multiply all these numbers together, you should get this. Okay, and then finally we can finally account for the second observation. So we can start from this and make an update on these beliefs using U2. That would give us P of R2 given U1 and U2. How do we do that? Yeah. Yes, thank you. So you have to swap R2 and U2.
Probability of U2 knowing U1 R2
Yeah.
times probability of R2 and U1.
No, not and. Condition on U1.
Condition U.
Okay? And that's proportionality. Oh, let me just use the same. This. Okay. Do we have this P of U2 given R2 and U1? Yeah.
Isn't E of U2 given R2?
Sorry?
Isn't U1 U2 independent of U1 given R2?
Yes.
Yes.
Which means?
E of U2 given R2.
Yes. Okay. Because of the conditional independence assumption that we have, this can be simplified to P of U2 given R2 times this factor. Okay, and now we have everything we need. This is given by this, and this is given by the sensor model. Okay. Okay, and this is F12. Questions? Yeah. Sorry? From there to there? You normalize. That's it. So you you sum these two values that give you normalization constant, 0.55, and then you divide each of these entries by 0.55, and you get this. And you see indeed that it's normalized. When you sum these two values, you get 1. Can I hide this to show the slides? No. Okay, so this is filtering. This is the base filter. You start from some prior beliefs, and then you integrate your sequence of observations by just iteratively first pushing forward through the transition model, and then making an update using the base rule. That's it. You just alternate between the two. Okay, so if we go back to our problem, with Pac-Man having to locate the ghosts to be able to chase them and kill them, well, you can do the same. You can assume some initial prior beliefs about the ghost positions, for example, uniformly at random somewhere on the grid. But then you will get these distance values at the bottom, which constrains the plausible positions. Okay? And now if you use that, so if you assume a transition model for the dynamics of the ghost, and you assume some sensor model that gives you these distance values, then you have everything you need to do filtering, so to estimate at any time step t the positions of the ghost given the observations, in this case of the force distances. All right? If you do that and then show the probability values directly on the maps, you would get something like this. Okay, where are the 4 ghosts? So you still have some uncertainty, of course, but it seems quite easy now to solve that game. Okay, this is just the base filter that you use to estimate the ghost positions, and then given these beliefs that you have, you can, for example, guide Pac-Man towards one or the other ghost. Okay, this is exactly what you will have to do in the second homework. All right. We have 2 more problems to solve, smoothing and yes?
In this example, every time on this case, we have to know how the ghosts are moving.
Sure, yes. You have to you have to assume a transition model, yes. Yeah. It could be that your assumptions are wrong also. But yeah, that's life.
The ghost have an AI to move to.
If your modeling assumptions are wrong, of course it will not work. Okay, like with every model. Okay, next, the smoothing problem, which is to try to estimate or to better estimate the value of the states in the past. Okay. So we want, in this case, to try to compute the probability distribution of xk given a sequence of evidence up to t, where t goes beyond k. Okay? And indeed, so if you have a system So far, in the filtering case, we assume that we were observing this, and all the ones before. and we are trying to estimate this. Okay? What we'll now be doing is we'll still be trying to estimate this, but given, for example, that we also observe this one. Does this bring any new information? About the fact of observing ET plus 1, does it bring any information about XT? Yes?
Yes, because we can infer on xt plus 1, which may give information on xt.
Yes. Okay. So in this case, what we have is a path which is non-blocking, so there is some information to be gained from this value. Okay? And so this is something that we can exploit then to properly compute P of xk given the sequence of evidence from 1 to t. Okay. So in the smoothing case, yeah, maybe I will do it slowly on the blackboard. Okay, so smoothing. We are interested in P of xk given observations from 1 to t. So the first step is that we can explode this set into the evidence up to k and the ones after. Okay, I'm just rewriting. Then this yeah. So using the Bayes rule, I can again rewrite this further into something which is proportional to. So I will be swapping these two. P of xk given 1k, that's my prior, times P of k plus 1 to t given xk and e. Okay? And again, because of the structure of my Bayesian network, I know that these variables are conditionally independent with this one given xk. So this can be further written as P of xk given k P of okay. Well, we know already half of this equation. This is the filtering term. So this is F1 to K. And I will call this other term b k plus 1 to t. Okay, so now the piece that we are missing is this one. We know how to obtain this by filtering. So p of e k plus 1 up to t given xk. So we know that the first evidence from this sequence, so ek plus 1, has not been generated by xk, but from some xk plus 1, okay, which we can reach by just doing one-step transition. So it is some xk plus 1, which we reach by some probability xk plus 1 given xk times, and now we can condition this to d of e k plus 1 up to t given xk plus 1, right? Xk plus 1 and xk. Sorry. And this simplifies to, just to make it explicit. Wait. Okay, so now we have p of xk plus 1. This does not change. Yes. Okay, and this. So there I can similarly explode this into ek plus 1 and ek plus 2 up to t. Okay? I'm just dividing this sequence into two terms, this first and then the remaining terms. Okay. Now this can be factorized into p of e k plus 1 given xk plus 1 times p of e k plus 2 up to t given xk plus 1. Okay, and what is nice about this equation is that, okay, this we know, it's the transition model. This we know, it's a sensor model. And this, do we know it? Actually, maybe not yet, but what you should notice is that it's the same as this one, but shifted by one unit into the future. Okay, so this we will obtain just recursively from previous iterations, provided that you iterate backward from the futures back to the present. Okay? And so this, if this was b k plus 1 to t, this one is b k plus 2 to t. Yes?
Question.
Yes.
When we do the k+2 and the x+1, we start the algorithm. Won't it go indefinitely?
No, because we have a limited sequence. We have
Limited sequence. It will stop at the last
yes.
sequence.
Okay. So now that with this. Okay, this was there. It's the same. So you see we arrive to this backward messages, which I express as this sum over the next value at the next time step of the next evidence times the transition times the backward message one step further into the future. Okay, which means that it appears that to compute b k+1 to t, I just need to evaluate some function which I will call backward, taking as input the beliefs of the backward message k+2 to t and the new and the evidence at k+1. Okay, so that's something we'll be able to do if we build these messages backwards, okay, from t to k and not from k to t. Okay, if you put all these pieces together, we arrive to the forward-backward algorithm, which you can use to both compute the filtering estimates and the backward and the smoothing estimates. Okay, so the idea is very simple. You start with some prior beliefs, as before, which correspond to the very first forward message f. Then we do one loop from 1 to t to compute the filtering estimates, x. So in this case, p of xi given evidence from 1 to i. So this for loop is what we've been doing with the filtering equations. And then you have a second loop which will go backwards from t down to 1. Okay? And at every step, what we'll do is to compute the backward messages from the one before, I mean the one after, but the one before in the loop. And then we will be combining these f messages with which we've computed in the very first loop together with what we've just computed. You multiply them together, you normalize, and then you get your smooth estimate. Okay? And that's it. There is no more twin than that. What is nice about this algorithm is that the complexity is just dependent on the number of time steps, so t. And if you just want, if you compute all the estimates for the entire time series, then that remains also linear simply with the length of the time series. All right, and then if you apply this to a problem with the weather equation, so let's do it. Okay, but so from before we have already computed these f messages. The first one which I've erased was f11, which was equal to okay, so we have these two messages. We basically run this forward-backward algorithm for half of the algorithm. We run the first loop. Now we can compute the smooth estimate to compute. And so our goal now will be to try to compute P of R1, let's say, given U1, and U2. Okay, so if we go backward, we'll have P of R2 given U1, U2 being equal to, I'm just here applying this equation, P of R2 given U1, 2, and P of U3, 2 given R2, okay, where this is F1, 2, and this is B3, 2, okay, which in this case I initialize to 1, okay. So that means this is equal to F, so this is equal to F1, 2, which is equal to these values. Next, we want P R1 given U1, U2, okay. And by our equation, we know that this is equal to P R1 up to that time step, so U1, times the backward messages, U22 given R1. Okay, that we know is F11, and this we don't know yet, but this would be B22, which we have to compute. And we have that PU22 given R1. Okay, so now we apply this. And so on. So in your case, we have k being equal to 1, so k plus 1 is 2. Okay, if you just try to apply this. And so we have to sum over the xk plus 1 values, so the R2 values. And then we do P of U2 given R2, it's this term here, times P of U32 given R2 times P, the transition now, P of R2 given R1. So that we know from the sensor model, that we know from the transition model, and this is the previous backward message, B32. Okay, so we know it. Okay, so if we put all of this together, we would have 0.9 times B32 times the transition plus 0.2 B32 times, okay, and this is equal to, after simplification, to okay. again, this is not a typo, even though these two values, they do not sum to 1. Okay, it's because now this table is a function of the conditional. Okay, and once with this, we'll just do it here. Okay, so now we can go back to this. P R1 even E1, E2, okay, which we set to be proportional to F11. Times the backward message now, which we've computed. And after simplification, you get okay. You should see the same number on the slide. Okay, if you follow the structure, we start from the prior, we project it forwards, we update, project it forward, we update. These numbers there, they correspond to the filtering estimates. And then we compute the backward messages from 2 to 1. And then we multiply these messages together with the filtering estimates, and we get the smooth estimate in the middle. Okay? Questions? Okay, let's take a break. We'll resume in at 10:40. That's fine with you? All right, we'll continue. Okay, so what we've been doing so far is to cover 3 problems: the prediction, the filtering, and the smoothing problem. There is one which remains for today, which is the problem of trying to estimate the most likely sequence of states, which I will call a trajectory, given a sequence of observations. Okay? So in this cartoon, for example, if let's say you are this agent, and you make 2 observations, that the window is broken and that some, how do we call this thing? And that the treasure is open. What is the most likely sequence of state transitions that could have led to this particular observation? Okay? So here we'll not be interested in the whole distribution of plausible trajectories, but just on the most plausible trajectory. Okay? Another example would be with the weather forecast problem. Let's say you do observe a sequence of true, true, false, true, true for the umbrella variable. Then a question you could be asking yourself is, what is the most likely sequence of states, in this case of the rain variables, which is compatible with this particular sequence of observation? Okay? So one very naive way would be simply to enumerate all possible sequences of state realizations, all possible trajectories, and then for each of them to compute the posterior probability of that trajectory given the evidence. Okay, you could do that, and if you can enumerate all of them, then you take the one which maximizes that probability and you return it. That would be correct, but unfortunately that can be quite inefficient because the number of trajectories will grow exponentially with the size of the trajectory. Okay, so here already with just a binary variable and sequences of made of 5 steps, we'd have 2 to the 5 sequences to evaluate, 32. And certainly there is a better algorithm than that. And indeed, you can obtain the correct answer using a linear algorithm by just doing one pass, one loop over the t variables. And the trick is to see that the most likely path, so if the goal is to retrieve P of x1 to t plus 1 given a sequence of observations. Okay, you want to find one, t plus 1. You want to find the sequence from 1 to t plus 1 of state variables, which maximize this posterior probability. Okay. So you can compute this if you realize that the most likely path, okay, is the most likely path leading to some particular value for the last variable, xt plus 1, which you fix, and that you have to reach necessarily by also the most likely path going from 1 to t, and then doing one more transition from t to t plus 1. Okay? And in equation, that's something that you can write in this way. So the maximum of the joint from 1 to t, and then including t plus 1, given a sequence of observation from 1 to t plus 1, is the most likely path going and reaching t, okay, which itself you have obtained recursively in this way, plus the transition, plus the update that you get from that you have to do to integrate the last observation. Okay, that's actually the same equation as for the filtering, except that we have replaced the sums by this max. Okay, but other than that, it's the same. Okay, and you can view that in this way with messages, which we replace now by this maximum over the conditional probability of 1 to t minus 1 and xt. Okay, I'm going fast on this because this is less important, and I still have quite some material to cover, so you can skip that when you will study the course. Okay, and then you have an algorithm to recover the most likely path from all these messages m that you can compute in this way. Okay, all right. So far, we've described Markov processes on arbitrary sets of state variables. We've not made any assumptions about these variables. In the book, they make so they refine the definition by saying that if you do assume that at each time step you only have one variable for the state and that this state variable is discrete, okay, so you assume that the domain of xt is some finite set of state values, which, for example, we could enumerate from 1 to s. And similarly, if you assume that the evidence variables are discrete, okay, so its domain is a finite number of values from 1 to r, then in this case, they redefine the class of model as what they call hidden Markov model. Okay? And why is this interesting is that when you make these restrictive assumptions, you just have one variable for the state, one variable for the evidence, they're discrete. You can actually rewrite the algorithms that you have seen in terms of matrix and vector operations. Okay, so how does that work? Well, if you assume that the same is a discrete variable, then you need a distribution over discrete values, okay, which you can represent simply as a vector made of big S elements, and each position in its vector corresponds to one of the possible values, and the numerical value that you associate with this entry correspond to the probability associated to that value. Okay? So the prior probability distribution over the states becomes now simply a vector of size S, okay, with positive numbers. Then the transition model, which is basically associating some starting value to all possible next values with some probability, becomes a matrix, an S by S transition matrix, okay, in which the entry at position ij, okay, corresponds to the probability that you associate to the transition starting in I and going to j. Okay, so you have S possible values for the states. You start in I, you may arrive in j, and you say you may arrive in j starting from S with the probability Tij. Okay, which is the same information as the one we had in the transition model, but now since everything is discrete, we can represent that as a matrix. Okay, and finally, we'll do the same for the sensor model. We'll redefine this conditional distribution of the evidence given the state now as an S by R sensor matrix, B, which will say that the conditional probability of observing J given I is stored at position ij in this matrix B. Okay? Now, how do we integrate the observations in this formalism? So you can instantiate an observation as a matrix OT. So this matrix will change for every observation that you make at each time step t. And you say it's a diagonal matrix whose elements correspond to the column ET of the sensor matrix B. So if you do observe, so if you have an S by R matrix, if you do observe, I don't know, the third possible value for the evidence among R of them, you pick the third column, okay, which has a size of S. You make this a diagonal matrix, and you say this is OT. Okay? And now if you use this formalism, the forward-backward messages becomes something very, very simple that we can write very compactly in this way. So the first equation corresponds to filtering, and you should realize that. You start from some belief that you just represent now as a vector over possible values of the states, F. Then you push it forward through your transition model by just multiplying by the transition matrix. And then you make a correction, you make an update, okay, given, in this case, by the observation matrix OT, or OT plus 1. And then you normalize, and you get the next message. And you can compute similarly the backward messages. So the backward messages are vectors that you can compute also recursively from t to k. And you say that to go from k plus 2 to t to k plus 1 to t, you take that backward message, you multiply it with the evidence, and then you do the transition. Okay? Maybe I can show you that. Okay, so we'll consider this example, which is the same as the weather problem, which we spent at least 20 minutes writing on the blackboard. But you can represent it compactly in this way. You assume an initial prior beliefs of 50-50. You encode your transition matrix in a matrix T, the same for the observation matrix. And now, since we'll do things on a computer, we'll assume that we have more observations, more than 2, let's say 5 of them. The 5, so the observation 1, 2, 4, and 5 are positive, and the observation 3 is negative. Okay, so we'll have now this sequence of observation matrices. So let me just go there. Pop, pop. Okay, so I'm just writing that in Python. Hop. So T, the transition matrix, the possible observations. And then I say that my initial belief is a column vector with 0.5, 0.5, that the observations will be true, true, false, true, true. Okay, and I will use these values to access the corresponding OT table. Okay, now a forward pass becomes very easy. Okay, let me maybe clear out outputs. So you start from F0, you multiply by the transition matrix or the transpose of the transition matrix, you make a correction using the observation matrix, you normalize, and then you get the first message, F11, which corresponds exactly to the values that we've computed. Okay, then we went one step further. We pushed it once more, then condition on the second evidence, and we got these values, which are the same as the one we obtained. Okay, except that I rounded them. It was 117, but we'll see. Okay, and we can continue. Now you do filtering to the fourth and the last message. And then if we do now the backward implementation, we start from the last message, which we initialize to a vector of ones. Okay, and then we implement the backward expression, where you multiply the backward message with the evidence and then with the transition matrix. We get these values. Okay, and now if you want to obtain the smooth estimates, we just have to multiply these two messages, the F messages with the corresponding backward messages. We really normalize, and you see I'm just doing really that. I'm multiplying F0 with B0, F1 with B1, and I normalize. Okay, and we would get this smooth estimate. Okay? So this is very convenient because very compactly we can represent the model in terms of vectors and matrices, and then the implementation of this algorithm becomes trivial. Just you see matrix and vector multiplications, which are implemented for you already out of the box in Python. Okay. You can also see if your system is discrete, and then you represent the distribution as a vector. Okay. You can also think about what would be the stationary distribution. So if you project forward your state infinitely many times, okay. So you could say, okay, what if I start in this initial state, 20%, 80%, and I use this transition model. So in this case, we could just do it manually. Okay, for example, I could do 10 push forwards, so from 1 to 10, and then at each iteration, I just take the current belief, which I project once by just multiplying by the transition matrix. Okay, and then I print. Okay, and you see that it seems to converge to something. If I do it 100 times, it goes on, and eventually reach this 0.5. Okay, so that becomes also trivial to compute, but actually, if you have that in the form of vectors, what we have is that F is equal to T transpose times F. Okay, that should remind you of your linear algebra. Okay, you can just compute now. You can solve for F. Okay, you will get a solution which corresponds to the eigenvectors of the transpose of the transition matrix. And if you compute them directly by just computing the eigenvector of the transpose of the transition matrix, you get this. And when you select the first one, you normalize, you get the same. Okay, without doing this loop, just use your knowledge from linear algebra, which allows you to directly find the stationary distribution. Okay? All right, so let's go back to the slides. Hop, hop. Okay, this is what I was saying with the stationary distribution, which you can get also very easily, in this case by identifying the first eigenvector of the transpose of the transition matrix. Okay? Questions on this? Okay, so if you've not followed what I've explained so far, now is the time to wake up, because I will tell you again exactly the same story, but using continuous variables. But you will see it's exactly the same. The notations are a bit more heavy, but if you have understood these two steps, we'll just be applying them now to continuous variables. Okay, so far we have, up to now, so in lecture 4, 5, and today 6, we have always assumed that the variables are discrete and that they're represented and that they have a probability distribution, which we can represent as a table. Okay? But in many cases, we will have variables that are continuous, they are not discrete. Okay? For example, if you want to, I don't know, let's say you have a robot somewhere and you want to track its position, you will not assume that the robot lives inside the grid world and that its position takes discrete value. In the real world, it would make more sense to assume that the position is a continuous variable. Okay, for example. Or similarly, the speed of this robot, certainly not 1 or 2 or 3, but it's a continuum of possible values. Okay? So how can we cope with this kind of variables? Well, we can extend our probability framework to have random variables that represent continuous quantities. Okay, the trick will just be to say that instead of mapping an element of the sample space omega to a discrete domain, we'll assume that now the domain of the variable is a domain which is uncountably infinite, like the real values. Okay? And when that happens, then we say that x is a continuous random variable. Okay? Now, if x is absolutely continuous, then its probability distribution will be described, instead of being described by a probability mass function table, will be described by a density function, lowercase p, which assign a probability to any interval, not to any specific value, but to any interval, contiguous interval in the domain of the variable. And we'll say that the probability that the variable, continuous variable, is within this interval will be given by the integral of the density function of the variable, okay, over the interval going from A to B. Okay? And then we'll say that P, or we will have constraints about the density function, and we say that it should be non-negative, so it can take either positive or 0 values, okay? And such that when you integrate this density function on the whole domain, so on dx, then the integral should be equal to 1. Okay? Are you familiar with continuous variables? Okay, good. So I will mainly describe two kinds of variables in this course. Uniform variables. So you assume that, in this case, the density function associated to the variable is the same everywhere on the support of the variable. So, for example, you could assume that the variable is anywhere in the segment, for example, from -2 to 2, okay, and cannot take any value outside of this interval. Okay? In this case, that can be formally described by a density which would be equal to 1 over the size of the interval if x is inside the interval, or equal to 0 if it's outside. Okay? The kind of variable we'll use in just a few minutes are Gaussian variables or normal variables, in which we'll say that that the variable can take any value on the real line, okay, from minus infinity to infinity, but we'll assume that it's mostly centered around some mean, mu, with some random deviations from that mean, which will be parameterized by a variance parameter. Okay? So the normal or Gaussian distribution, which I will denote as n, defined by two parameters, a mean and a variance, is described fully by a density function which takes this form. So it's just a normalization constant times a positive function, so in this case the exponential, of minus the squared of the deviation to the mean, okay, rescaled by the variance. Okay? Are you all familiar with that also? Okay. Are you then familiar with the multivariate normal distribution, where we have normal distributions over vectors, not just scalars? Okay, so you can generalize that. For example, here on the figure to two dimensions, you'd have distributions over vectors of two elements. And so you can define a multivariate normal distribution in the same way. You need two parameters, a mean and a variance, except that now the mean will become a vector, in this case, for example, of two elements, and the variance will become a matrix, which strictly speaking we call the covariance matrix, which will be, in this case, for the two-dimensional case, a 2x2 matrix. Okay? Where each entry will correspond to the covariance between any two elements in your vectors. Okay? And again, it takes the same shape. It's a normalization constant of times an exponential of minus a deviation to the mean, a square deviation to the mean, rescaled by the covariance. Okay? All right. In what we'll consider next, so we'll consider states, okay, and beliefs which will represent as normal distributions, multivariate normal distributions. Okay? And we'll make first assumptions about the transition model. We'll assume that the transition model is linear plus some Gaussian noise that you add to it. Okay? And maybe I should explain that later. Okay. So we have this multivariate normal distribution, which we define by M and the covariance. Okay, which you can, for example, represent in this case. Let's say that we have a two-dimensional Gaussian distribution over vectors of size 2. We'll call the first element x, the second y. Okay. So now we'll have a normal over vectors defined by two parameters, a mean vector made of two elements itself, A and B, and a covariance matrix made of four elements, A, C, C transpose, and B. All right? Then there is something you should know, is that if you take a multivariate Gaussian distribution and you marginalize out some of the variables, any one you want, the remaining marginal distribution will be a Gaussian distribution. Okay, so the marginal distribution of a Gaussian, or any marginal of a Gaussian, is a Gaussian. Okay, and the parameters associated to these marginals are just the parameters corresponding to the entries that you keep. So, for example, if you have this 2D Gaussian distribution and you want to obtain the conditional over x only, the marginal over x only, then what I'm saying is that P of x is itself a normal distribution where the mean corresponds to the mean associated to x, so A, and the covariance corresponds to the sub-block associated to the variables that you keep, A. Okay, and mathematically, we just have that. P of the marginal for x is just a normal also of parameters A and covariance bk. The same for the other marginal, Py. You just subselect the entries and the corresponding parameters. So Py would itself be a Gaussian. parameterized by B for the mean and by capital B for the covariance. So any marginal of a Gaussian is a Gaussian. And what is also very interesting is that any conditional of a Gaussian is itself a Gaussian. Okay? So for example, if you start from this joint and want to obtain the condition of y given, the condition of x given y, it would be itself a Gaussian parameterized by this mean vector and by parameterized by this covariance matrix. And vice versa, if you want the other conditional py given x, it would itself be a Gaussian parameterized by this other mean vector and this other covariance matrix. Okay? The next expression we'll need is that if you have a marginal distribution Px, which is Gaussian, which you parameterize by a mean vector M and some covariance matrix P, and then you have also a conditional relationship going from X to Y in the form of a conditional Py given X, and you say that this is itself a normal distribution, which means it's a linear combination of X. Okay, and the covariance is R that you fix. Then you can compose this marginal and this conditional to obtain the joint. Okay, so that will be useful for us because what we'll assume is that we have some belief Px as a Gaussian, that we have either a transition or a sensor model as a linear Gaussian distribution like this one, and then we'll be able to recover the joint from this, okay? And you can recover the joint using this expression that you see there. So the joint of x and y, where when you define them in this way, will correspond to this mean vector and this covariance matrix. Okay? So these are just properties that you may assume you have access to or that you remember. Okay, I will not make you study these formulas, but you should be able to use them if I give them to you. Okay, so now that we have set this, now that we have defined continuous variables and multivariate Gaussian distributions, we can define what we call the continuous base filter, in which what we want to do is to solve the filtering problem when all the variables are continuous. Okay? And so now the filtering equation, which was this one in the discrete case, will become this equation. Okay? And you should not be afraid, it's just the same equation. We have just rewritten the sum using integrals, because integrals are just infinite sums. That's it. And also, yes, we have replaced this capital P, which corresponds to probability values, now to lowercase p, because we have continuous variables, so we should deal with the density and not the probability associated to the variables. Okay? So you have the same P of xt given a sequence of evidence up to time t plus 1. How do you do that? You start from your prior belief, which you've obtained from previous iterations. This is a filtering estimate. You push it forward once through your transition model, except that now you would need to consider infinitely many starting state xt. Okay, but assuming you can, you solve this integral, then you obtain some probability distribution of P of xt plus 1 given observations up to t, and then you make a correction, okay, exactly like here, to account for the evidence et plus 1. Okay? And the normalization constant now would become something like this because we have continuous variables. Okay. So generally speaking, you will not have any analytical or even tractable expression for this continuous base filter unless we make assumptions about the variables. And the assumptions that we'll make is that first we have a Gaussian prior. So we'll say that P of x0 is defined by a Gaussian distribution. Your prior beliefs about the initial values of the system would be a normal distribution about x0, parameterized by some mean, let's call it mu0, and some variance or covariance sigma squared 0. Okay. That's the first assumption. Second, we'll make an assumption about the transition model. So P of xt plus 1 given xt. Again, pay attention, I'm using lowercase p everywhere now, okay, because they are no longer probability values, they are density values. And I will say that P of xt plus 1 given xt, okay, is parameterized by a mean, okay, which is a linear projection of xt. Okay, so xt multiplied by some matrix plus some offset that you define. Okay, and the covariance is something fixed to sigma x. Okay, and so that defines the distribution over xt plus 1. And finally, we'll make a similar assumption about the sensors. We'll say that P of et given xt is normally distributed around the mean, which is given by a linear projection of xt plus some offset d, and the covariance is something you set and say to sigma e. Okay, so technically we say that we have a Gaussian prior, that we have a transition model which is linear Gaussian, and the same for the sensor, we make a linear Gaussian model assumption. Okay? And what is nice now is that because of these assumptions and because of the properties of the Gaussian, everything will remain Gaussian. And so we'll have a tractable form to compute and update the posterior. Okay? And when you do that, what you obtain is the Kalman filter, which is something as engineers you should all know. To me, it's as fundamental as quicksort for computer scientists. This is something that is used everywhere in, for example, in space missions to track shuttles and many other applications. Okay, Kalman filter, so how does it work? We make this assumption, okay, and then we'll just do filtering as before. Okay, we'll do the continuous base filter, but under the assumption of the Kalman filter. Okay? So, again, what do we have to do? We have to project, predict, and then update. That's it. A prediction step will be a push forward of some initially Gaussian prior through your linear Gaussian transition model. Okay? So P of xt plus 1 at the next time step given observations up to t. You start from your initial beliefs, you project it once to the next time step, and then you marginalize out xt. What is interesting is that if this is Gaussian and this is Gaussian, then the joint is Gaussian. And then when you do the integral, what you are effectively doing is that you are computing a marginal of a Gaussian. But I've told you the marginal of a Gaussian is a Gaussian. So that whole thing is a Gaussian distribution. And similarly for the update is that you start from the projected belief at the next time step, P of xt plus 1 given observations up to t. We know it's Gaussian. And then we'll multiply this by another Gaussian distribution, a linear Gaussian distribution. That's because of the assumption on the sensor model. Gaussian and Gaussian together form a Gaussian. Okay? And effectively, here what we would be doing, because we are normalizing, is that we have this joint distribution P of xt plus 1 and et plus 1 given e from 1 to t. This joint is Gaussian. And then we condition on et plus 1. Okay? When you take a joint Gaussian, you condition it, you obtain another Gaussian. Okay? So this term on the left is also a Gaussian distribution. Okay? Which is very, very convenient because if we know everything will remain Gaussian, the only thing that we need to compute are the parameters that we associate to these Gaussian distributions. So we just need to maintain a mean and a covariance parameter. If we have that, then we have everything we need. Okay? Because we know everything is Gaussian. Okay? Well, this is exactly what I've just said. For the Kalman filter, this filtered distribution will be a multivariate Gaussian distribution of some mean ut and some covariance sigma t. This is true for any t. Okay? Therefore, if I want to do updates with the Kalman filter, what I need to find is how to update mu t and sigma t. Okay? Is it clear for everyone? Okay, so let's take a very simple example. We assume that we have some, I don't know, a robot, okay, which you cannot locate exactly, and it's a robot on just a one dimension. And this robot, you assume initially it's somewhere centered around around mu0, but you don't know, you are not certain about that. So you allow for some dispersion around this mean, which you specify by this variance parameter, sigma squared 0. Okay? Then you assume a dynamic for the robot. You assume, for example, it makes random moves to make things simple. So it's not moving towards something, it's just making random moves. And so when you say that, one possible way to specify the transition model would be to say that the next position at t plus 1 is a random position centered around xt with some Gaussian noise, Gaussian perturbation of variance sigma squared x. Okay? You don't see the robot, you only have access to noisy measurements of its actual location. Okay? But again, we'll make a linear Gaussian assumption for that sensor model, and we'll say, for example, that your observations are centered around the actual position xt, which you don't observe, plus some noise specific to the sensor. Okay? Okay, then let's say there is one time step which happens. In this case, we would need to go from the prior p of x0 to p of x1 before observing E1. You can do everything by hand, or you can just use the properties that you have there, this one and this one together, and you should arrive to the conclusion that after one step through the transition model, your beliefs about the actual position at time step 1 should be still centered at 0, but now the variance is larger. Okay? You have the initial variance plus the variance due to the random transitions. Okay? Then you do observe a noisy, you collect a noisy observation of x1 as E1. And so in this case, you start from your Gaussian beliefs, which you've computed in the previous slide. Then you make a correction. Okay, so you do the Bayes rule, you simplify, or if you can say you simplify, and you arrive again to a Gaussian distribution where the mean is given by this expression and the variance now is given by this expression. Okay? And so when you plug all these things together, you arrive to these two equations that you need to use to update the parameters of your belief state. Okay, mu t plus 1 is equal to this expression involving your previous belief ut, okay, which you rescale by the variance of the evidence. Then you add the observation, which you rescale by the sum of the variance of the transition and the initial variance, and then you normalize. Okay, and the covariance becomes this expression. So these equations, even though they may look a bit difficult to parse, they actually do make sense. So for example, if you say that your sensor is not very reliable, which would mean that the variance term here is large, then certainly you should not in this case take into account the evidence too much to update your beliefs about the position. Okay? But this is exactly what will happen. If the variance is large, of the sensor is large and dominates these two variances, then this term will be larger than this one, and after normalization, you will just remain close to initial beliefs ut. On the other hand, if you do trust your sensor a lot, then the variance here will be small because you have very accurate measurement, low uncertainty. In this case, this term would not dominate the other, it would be this one. And so in this case, you would almost update the mean to the actual observation that you have. And this is what would happen when you have a perfect sensor eventually. Okay? All right. So this is for the one-dimensional case. Okay? You can do that in n dimensions. And you derive to this equation. So now if you assume that we have a linear Gaussian transition model in this form without the offset term, and we have a linear Gaussian sensor model, then you do exactly the same. You use the properties of the Gaussian, and you derive to these equations to update the parameters of your beliefs, but now over n-dimensional vectors. Okay? And again, all of this should make sense, right? Because let's take, for example, this one. This one means that after projection, mu t plus 1 is mu t that you push forward through your transition model, f. Okay? But maybe you make a correction, okay, by integrating the observation et plus 1. Okay? And what you use is the difference. So you have mu t, which you push forward. That gives you mu t plus 1. Okay? And then you can also compute the expected value of the evidence, okay, which you would get by multiplying mu t plus this term further by the sensor matrix H. Okay, so this term, in a sense, corresponds to the expected observation at the next time step. And then you just consider how far you are from this expected next observation. Okay, and then you use that to make an update to mu t plus 1. Okay, and I will not try to explain these other expressions. But even though they may look scary, okay, really, it's just these two operations. Okay. Okay, so this algorithm, the Kalman filter, is actually quite old. It was invented in the 50s by Kalman. And the first and main application of that was in the Apollo guidance computer. So the shuttle which arrived to the moon and back. And so in this computer, the Kalman filter was used to track the position of the shuttle as it went into orbit around the Earth, and then transition towards the moon and back towards the Earth. So you get what you want, of course, is to know the position of the shuttle, okay, to make maybe correction to the trajectories, but you can't measure the exact position. Okay, so the Kalman filter in this case was used to basically estimate at every time step the current position of the shuttle. Okay. And you do that exactly using these equations. And if some of you are curious, you can follow this link. It's the Apollo 11 source code, so the actual program which ran in this computer, and you will find an implementation of the Kalman filter in assembly, but still an implementation of these equations. Okay, and there you have another picture showing more or less the same thing. So you would have noisy measurements, and from these noisy measurements, which you see with the dots in turquoise, you would estimate the actual positions. This would give you the guess in red, and in blue you would have the actual trajectory. Okay. Another, in my opinion, very interesting and important application of the Kalman filter or filtering in general is weather forecast. And so I don't know if some of you have already been thinking about how do we actually do actual weather forecast. Not umbrellas and rain and no rain, but okay, so think about, I mean, as scientists or engineers, how would you solve this problem? So what is a forecast, a weather forecast, really? A weather forecast is a projection into the future of the state of a system, which we call the Earth, okay? So you can Okay, so how do we predict the weather? Well, basically, you can view the Earth as a system which we don't observe fully. Okay, so let's say this is the Earth. Okay, in 3D, and what we would like to do, is to describe the state of the Earth. And specifically for weather, what could be interesting is to try to estimate the state of the atmosphere, for example. Okay. So that's just a big volume, okay? And what you want to know is that at every possible location in this volume, you would like to know some physical variables like the temperature, the speed of wind, the pressure, I don't know, the moisture, and all other things that you could think about, okay? So you can imagine that you have this 3D volume, which you discretize into a big grid, okay? Because you will not be able to model this thing at every microscopic position, but let's say you have a grid. Like this. And at every node of this grid, you have some physical variables. Okay? Okay? And if you summarize all of these variables at all these possible locations in your grid, what you have is a description of the state of the system at some time step. Okay? If you knew all the values of all the variables at every position, then you can use physics to predict what will be the evolution of weather. Okay? You can say that, okay, at the next time step, I will have xt plus 1, and you would go from this to there, assuming a transition model, going from xt to xt plus 1. Okay, so if you just consider that the atmosphere is just a big volume of fluid, for example, you can use fluid mechanics. You put your knowledge about fluid mechanics, Navier-Stokes, all you want inside this transition model, and you can use that to simulate what would happen if you start from xt, you do one time step, and where you would arrive at t plus 1. Okay, so you can use your physics knowledge to do the transition. Okay, so we may have also other previous values, xt minus 1, and so on and so forth. However, we never observed this big volume of all these variables. Okay, the only measurements that we have are very sparse and noisy measurements. For example, maybe there we have a weather station, and we measure very locally the temperature of wind, the pressure, the temperature, the speed of wind, and other physical variables. And we may have quite a few of these weather stations around the globe, okay? But we'll never be able to cover the entire planet with weather stations at every possible location. We may also have satellites, and we do have satellites, which will cover usually a band like this. As they pass over that region, they will be able also to measure some of these physical variables. Okay, but even with satellites, you don't have a full picture of the state. Okay, so that means at every time step t, I have observations in t. Satellites, weather stations, other things. Okay. And you may understand how your instrument works. Okay, you may understand how a thermometer works in your weather station. I think that's quite reasonable. You may also understand how your satellite works and the kind of measurements it makes. So you may have a reasonable knowledge about P of t given xt. All right? So now if you want to do weather forecast, what you would need is to know xt fully. If you knew xt fully, you would just use Navier-Stokes, simulate the future. Okay, and you would have weather forecast. But the big problem is to estimate the current state, given past observations. Okay, so the big problem is to solve this. So to determine the conditional distribution of xt given observations up to t. That's a filtering problem. Okay, the issue is that in practice, for such high-dimensional states, you will not be able to represent that as a whole distribution, just too large. So we have to approximate this. And so one possible approximation is to say that instead of trying to estimate this entire posterior distribution over all possible configuration of the planet, I will just find the most likely, for example. So the value xt for which this posterior density is the largest. Okay? You can also make further assumption about the shape. You can assume that this thing is Gaussian, okay? Which usually will not be the case because the transition model and the sensor model are not linear Gaussian in reality, in the real world. Okay, but if you make this further assumption, then you can actually build a quite good estimate of the states, and you would arrive to an algorithm which is called 4D VAR, and which is the algorithm which is used in weather forecast. Okay, so I will show you that. They will re-explain that, not exactly in the same way, but you will see that what we have seen today on this toy example is actually useful for real problems, like predicting the weather.
4DVAR stands for four-dimensional variational data simulation.
A numerical weather prediction is an initial state problem. We need to know as accurately as we can the initial state of the atmosphere if we want to have any chance of making accurate predictions.
We first run a short-range forecast, and then we wait until we receive all the observations within an assimilation window. Once we have received all the observations, we go back at the beginning of the time of this window and we adjust the previous forecast based on all the received observations. So retrospectively, actually, we go back 12 hours and readjust the previous forecast to do an analysis of the last 12 hours. And from that on, then, we start running the forecast once we're happy with the result.
4DVAR is the only tool we can use to bring together these observations to build a consistent, physically reasonable state of the atmosphere from which we can launch successful forecasts.
It took almost 10 years from the 80s to the 90s, but we implemented 4DVAR in November 1997. So November 2017 marks the 20 years anniversary of the implementation of 4DVAR at ECMWF. It was very much pushed by the academic community, and in particular the French academic community.
I've been interested in this question of taking all observations over a period of time, say 12 hours, and combining all this together with a numerical model which computes the evolution of a certain atmosphere. We showed that this technique could be applied to meteorological problems. And it became four-dimensional variational assimilation, 4DVAR. We went for a meeting at ECMWF, we presented the work, and they were very interested, and they took the decision to develop 4DVAR for the model and for the prediction, to use it for real meteorological prediction.
In the near future, there will be a very large class of new types of observations. They involve radar measurements, LiDAR measurements, even lightning measurements.
These hundreds of millions of observations need to be brought together in a consistent way, and 4DVAR is the only system that can do that. Now, 4DVAR can take information from a satellite, for example, which might be telling us about humidity at maybe 9 o'clock, and it will compare that information with what the satellite tells us at 9:30 or at 10 o'clock and see how that humidity has changed. And it can interpret those changes of humidity not in terms of adding moisture or reducing moisture, but in terms of the wind, which has made that humidity maybe move from one place to another. And so 4DVAR is the only system that can use humidity observations to derive wind information about the atmosphere. And this unique feature is called wind tracing. 4DVAR is being applied into worlds that it was never envisaged to be applied.
In the next 20 years, or at least in the next 10 years, we want to include more components.
So the next thing that has been added to 4DVAR has been an ensemble component, which is used to estimate the uncertainty of the initial estimate that we have. Better knowing the uncertainties improves the actual estimate of the state.
And then we also want to go to higher resolution. So we would like to run an ensemble at 5 kilometers in 10 years' time or so.
4DVAR is, I think, acknowledged the best system in the world, but it will need continuous support. It will need continuous support scientifically from people improving, developing it. It will need support from the member states to provide computing facilities and resources. But whilst that is in place, and there's no sign that that's going to go away, and the future is bright with 4DVAR.
Comments? Yeah, maybe just one more piece of information. So it looks fancy and everything, but why do we still have so bad weather forecast? So if I go back there, and this is something they alluded to, but they say it would be nice to run this thing at very high resolution, meaning the mesh would be very high resolution. Currently, you should understand that for doing actual operational forecasts, the size of this square, can you guess what will be the size of the square as used now to do actual forecast? If this is the whole Earth, yes?
10 by 10.
Who says less? Who says more? Yeah. So that means we would have maybe 3 squares to cover the weather for Belgium, in your case. Actually, the size of this square currently is 28 by 28 kilometers. Okay, so everything inside the square is assumed to be homogeneous, so the same. Of course, then you can understand why it's imprecise sometimes, because we are making coarse approximation of reality. If we want to increase the resolution, to reduce the size of the square, then that problems become even more difficult to solve. Okay, because this will just blow up. And then another thing that they said is that, okay, they are doing this ensemble to account for uncertainty. So for decades, they've been just using the one point estimate of the state, okay, the one that maximizes or approximately maximizes this. You can have several estimates like this, like 5, 10, and all of them together, you can assimilate them as an approximation of the whole distribution. Okay, but so far they are also using very few of these ensemble members, so the size of this ensemble remains small. So the uncertainty remains very poor. But of course, if you know that you can't estimate this precisely, you'd better account for the uncertainty that you have, if you want then to make forecasts in which you can rely. Okay, but so far they are not really doing that much. Okay. All right, what time is it? Okay, there is a few more slides, but I think I will skip them. I've talked for long enough. I will briefly flash them so that you know this exists. So these models that we have considered, usually with one variable for the states, can be generalized to many variables that are connected to one another according to a structure which you specify, for example, in the form of a Bayesian network. And you can also define transition from one time step to the other, from a set of variables to another set of variables. Okay? This is what you call a dynamic Bayesian network, okay, because you will have several variables which evolve through time. And again, you will have also a set, and you will have similarly a set of evidence variables instead of having just one of them. So this is just to say that everything can be generalized to this. When is this useful? Well, there are many scenarios in which you would define a system as a collection of variables that evolve together, and you also observe this system through various instruments. One obvious application, for example, is the case of ICU monitoring. So if you are at the hospital, you are critically ill, then usually you are connected to all these machines. These machines will be collecting observations about various things like the heartbeat, the saturation in oxygen, and many, many other things. Okay, so these are just noisy measurements of your state, your patient state, okay, but you only observe that. But you can start making assumptions, describing things as this system from which you estimate this or that, and then compose all these time series to make then guesses about other important variables that, for example, physicians care about, and so on. You can have algorithms to do exact inference. It does not scale, basically, so that does not work. But what is very interesting is this particle filter. So it's a very powerful algorithm which you can use even when your transition and sensor model are not necessarily Gaussian. Basically, as long as you can sample from your transition model, you can simulate random transitions, or you can simulate random observations, and also you have access to the density of the observations, then you are good to go. You can do particle filtering, and it's very, very simple. You start from your initial beliefs, which is a distribution. Okay, but now it's no longer a Gaussian distribution. So how do you deal with that? You can't just store a mean and a covariance. What you do is that you represent this distribution as a set of realizations, which you call particles. So you draw many times from your initial priors, let's say 1,000 times. You have 1,000 realizations. You call that, that corresponds to your representation as particles of your initial distribution. Okay? And then in a particle filter, you want to maintain an accurate estimate of the current state given observations. How do you do that? You take your particles, you push them forward to your transition model, you reweight them by how well they explain the new observation, you resample, and you get a new distribution in the form of particles representing the filtering distribution. And that scales to very high dimensions. You can use, this is very popular, for example, in robotics. Every time you have a robot which has to locate itself given noisy measurements, for example, distances to walls and many other things, you can use this algorithm to build a good estimate of the robot position. Okay, so it works like this. I will just keep it. This is the algorithm. What you see is that you start from a prior, then you sample many times from the transition model, then you reweight your samples by the evidence, and then you draw with replacement your particles. That's it. Okay? So no complicated Gaussian expressions, just 3 lines, and you get a very good estimate of the posterior. Okay, so in summary, we've covered today temporal models, which are models relating a state of a system evolving through time to observations. We have made some assumptions to make these inference problems tractable. So we have seen how to solve the filtering problem, the prediction problem, the smoothing problem, and the problem of determining the most likely sequence. And really the core idea which you should remember is that everything is just a composition of these 2 steps. You have some initial prior distribution, you push it forward, you make a prediction, and then you make a correction with the observation that you have. Really, that's it. Questions? Okay, thank you. Oui.
Faire des hypothèses sur l'adversaire et si par exemple il y a plusieurs l'adversaire dans notre projet, on va faire plusieurs hypothèses.
Ouais.
Et puis troisième
Ouais, bah, oui, mais c'est juste un composant de ton algorithme qui va changer normalement. Ton algorithme, telle implémentation, on devrait rester générique et tu swaps simplement le modèle de l'adversaire pour l'une ou l'autre chose.
Dans le même algorithme.
Ouais.
Pour le projet de jeu, on est clairement sur un cas où on pourra faire l'optimisation de la code discrète.
Ouais.
On pourra ajouter quelques matriciels.
Ah, au principe, ouais. Ouais. Mais c'est pas linéaire gaussien. Ouais. Ok. Oui, oui.
Le projet
Oui. Attends, je vais juste couper ça avant de...